The tech industry has a labeling problem. The term agent is currently applied to almost any piece of generative AI, stripping the word's engineering utility. A large language model that answers a prompt and immediately forgets the interaction is highly complex, but it lacks agency. A large language model, or LLM, is an AI system trained on vast amounts of text to predict and generate human-like language. An LLM operates strictly on request and response. Meanwhile, a simple non-player character in a video game that navigates a maze and remembers dead ends actually possesses agency. To fix this bottleneck, the AI Metaverse Working Group released their version 1.0 standard. This version establishes the specific architectural boundaries required for entities to operate in blended physical-virtual environments. This diagram illustrates the baseline standard for autonomy. On the left, we see a standard linear pipeline: prompt, output, stop. On the right is a continuous loop. The defining characteristic of an autonomous agent is not the presence of machine learning, it is the closure of the perception-action loop over time. As the linear model fades, we see the continuous cycle in action. Under this standard, a basic rule-based system qualifies as an autonomous agent, provided it continuously evaluates its environment and exercises discretionary action selection based on its own internal state. The true test of agency requires a system to maintain a persistent structural coupling with its environment. It must dwell within a space and react to it over time, rather than just executing a single command and shutting down. This continuous dwelling is defined in the standard as ontological presence. An agent must exist continuously within a system. This flowchart diagrams the four-step temporal closure cycle established by researchers Franklin and Gracer. The cycle begins when past actions exert force, altering the environment node. Those alterations directly dictate the data ingested during future perceptions. The agent consumes an environment it helped create. This entirely drives the action selection paradigm. An agent's primary computational function is solely to produce the next appropriate action based on that incoming data. To decide on that action, the system continuously recreates and references its own internal memory of past interactions to inform its current choices. This cyclical adaptation is distinct from predefined scripts or direct human proxies. A script follows a hard-coded path regardless of environmental shifts, and a proxy simply translates human input without independent processing. By closing this temporal loop, the software transitions from a reactive tool waiting for input into an entity that actively participates in the environment's causal chains. To execute this continuous loop, the standard mandates a specific structural baseline. Every true autonomous agent must implement a precise 5-layer minimal architecture. This diagram shows the architecture required by the standard. At the base, the sensory interface samples data, passing it up to state management memory banks. Next is the motivational structure, strictly separated from action selection logic. Finally, feedback processing officially closes the perception-action loop. This identical 5-layer structure is required regardless of scale. It applies equally to massive server-hosted ecosystem simulators and lightweight client-hosted personal copilots running on a mobile device. Advanced capabilities like social cognition, theory of mind, or complex multi-step scheduling are classified strictly as optional extensions, not baseline requirements. If an engineer omits any of these 5 interconnected layers, the system degrades. It drops to a level 0 or level 1 advisory tool and fails the standard for autonomy entirely. Operating within a fully digital environment is relatively controlled, but the framework faces a specific complication in mixed reality. Mixed reality, or MR, is a technology that anchors virtual objects to the real world and allows them to interact with physical environments in real time. Here, agents must operate across a blended physical-virtual boundary. To handle this, the standard enforces the principle of coherent behavioral continuity. An agent's logic must simultaneously process synthetic virtual objects and real-world physical constraints without breaking state. Returning to the diagram, the minimal architecture expands laterally for physical space. The spatial computing layer generates continuous wireframe meshes. Next, the reality compositor calculates occlusion and collision physics, so the agent respects physical boundaries as objects pass behind real-world barriers. These layers enable persistent spatial anchoring, tying memory to physical coordinates across user sessions. Because this requires continuous camera feeds, the stack includes a privacy manager layer, using geofences to block incoming visual data from restricted areas. To comply with spatial privacy standards like the GDPR, this layer prioritizes on-device processing. The GDPR, or General Data Protection Regulation, is a strict European privacy law that governs how personal and biometric data must be collected and processed. By mapping environments locally, the architecture minimizes the transmission of sensitive physical space data to the cloud. Finally, the lateral stack includes the safety monitor layer. This module enforces physical hazard detection and explicitly limits the cognitive load placed on the human user. The safety monitor dictates emergency behavior overrides. If a user engages in rapid, unsafe physical movement, the safety monitor triggers an override, rendering the agent transparent to prevent physical collisions. Spatial agency requires a system to dynamically map, respect, and bound its logic within the physical realities of the human user. This is the complete classification schema, providing the standardized technical fields required for developers to govern and move these autonomous entities across platforms. Profiling an AR Navigation Assistant shows this deployment. The schema populates host actor is hybrid, control level is 2, embodiment is spatially anchored. Sliding this control from 0 to 4 defines escalation triggers, setting exactly when the system asks permission. By strictly mapping the perception and action flows, engineers establish auditable boundaries for infrastructure platforms. Defining these precise hardware and spatial limitations allows an agent to maintain its state and safely migrate across different virtual worlds or physical locations. The implementation of these architectural layers and schemas allows for the deployment of persistent, stateful entities that navigate blended realities. This shift from static tools to governed autonomy provides the structural foundation required for a functionally integrated metaverse.